The world around us is in this state of constant transformation. Milk goes sour, iron rusts, you cook an egg, and it all seems, well, kind of like everyday magic, doesn't it? But it's not. It's chemistry, this hidden world of change that's happening right under our noses. So let's pull back the curtain and see what's really going on.
Really think about it for a second. When you light a match, or bake bread, or even just take a breath, something fundamental is changing, right? You're starting with one thing and ending up with something totally new. What is actually going on there on a level that's way too small for us to see?
Well, every single one of those examples is what we call a chemical reaction. It's this incredible process of just rearranging atoms. Old connections break, new connections form, and you get entirely new substances. It's literally the engine that runs our world, from how we digest our food to how stars are born. And here's the cool part. These secret chemical changes, they don't happen without a trace. No way. They leave behind all sorts of observable clues, almost like a trail of breadcrumbs. And if you know what to look for, you can basically become a chemical detective, spotting these reactions happening all around you.
Okay, so what are these clues? How can we be 100% sure that a chemical reaction has actually happened and not just some physical change, like ice melting into water? It's time to open up our detective's toolkit.
So there are four main signs you want to look for. First up, a change in state. Imagine mixing two clear liquids together and suddenly a solid cloudiness appears out of nowhere. That's a huge clue. Second, a change in color. This one's super obvious, right? Like when a shiny iron nail gets that dull reddish-brown coat of rust. Third is the evolution of a gas. All that fizzing and bubbling when you drop an antacid tablet in water, total giveaway. And finally, a change in temperature. If a reaction suddenly makes its container feel hot or icy cold all on its own, you can be pretty sure you're looking at chemistry in action. Now, trying to describe all of this with regular words can get, well, a little long and clunky. So chemists, being pretty efficient folks, came up with a special kind of shorthand to describe exactly what's happening. It's almost like learning to crack a secret code. Okay, so take this description. When a magnesium ribbon is burnt in oxygen, it gets converted to magnesium oxide. It's perfectly clear, but wow, is that a mouthful? Imagine having to write that out every single time you wanted to talk about a reaction. There's got to be a better way, right? And here it is. This is the solution. We can streamline that long sentence into what's called a word equation, which is better, for sure. But the real power, the real elegance, comes from the chemical equation. Mg plus O2 to MgO. It's short, it's universal, and it is packed with information. This right here is the language of chemistry. But when you're writing in this new language, there is one absolutely 100% unbreakable rule. You can't just have stuff appear out of thin air or vanish into nothing. Everything has to be accounted for. You have to keep the books balanced. This big rule is called the law of conservation of mass, and it is a cornerstone of all science. What it means is that whatever atoms you start with on the left side of that arrow, we call those the reactants, you have to end up with the exact same number and type of atoms on the right side, the products. They just get shuffled around into new partnerships. And that's exactly why we have to balance equations. Take a look at this reaction between iron and steam. On the left, we start with one iron atom, but on the right, we end up with 3. And we start with 1 oxygen, but end with 4. This is what's called a skeletal equation, and right now, it's breaking the law. We've got to fix this. And check this out. By adding these big numbers out front, we call them coefficients, we can balance the books. Now look, we have 3 iron atoms on both sides, 8 hydrogen atoms on both sides, and 4 oxygen atoms on both sides. Perfect. The law is satisfied, and the equation is now balanced and correct. Okay, so now that we have the language and the rules down, we can start to see some patterns. And it turns out that a huge number of chemical reactions fall into one of just 4 main types. You can think of them as chemistry's key moves. So first, you've got combination, where 2 or more things come together to make one new thing. The exact opposite of that is decomposition, where one big thing breaks apart into smaller pieces. Then things get interesting with displacement, where one element basically cuts in and kicks another one out of a compound. And finally, double displacement, which is kind of like 2 couples swapping dance partners. Let's see each of these moves in action. All right, here's a classic combination reaction. If you add water to something called quicklime, they combine to form just one single product, calcium hydroxide. Two things become one. Simple, direct, and this one also happens to release a lot of heat. Next up, the opposite move, decomposition. If you heat up these green ferrous sulfate crystals, that one single compound literally shatters into 3 simpler products, ferric oxide and 2 different sulfur oxide gases. See? One thing becomes many. That's decomposition for you.
Ah, this one's a famous experiment. If you dip an iron nail into a bright blue copper sulfate solution, the iron, which is more reactive, displaces the copper. It basically muscles its way in. So the iron goes into the solution, turning it green, and the copper gets kicked out and coats the nail. One element gets swapped for another.
And here's where both compounds swap partners. When you mix solutions of sodium sulfate and barium chloride, the sodium and the barium trade places. This creates barium sulfate, which is this white solid that just appears and falls out of the solution. We call that a precipitate. And good old sodium chloride, or table salt, which just stays dissolved in the water. Okay, let's bring all these ideas back home and look at one of the most important and common types of reactions on the entire planet, one that affects us every single day, oxidation. It's all about how different things react with oxygen. And oxidation has 2 faces you're probably very familiar with. On one hand, you have corrosion. This is the oxidation of metals, like when iron reacts with oxygen and water to form rust. It's the slow, destructive process that damages everything from our cars to massive bridges. And then, on the other hand, you've got rancidity. This is what happens when the fats and oils in our food oxidize. It's the reason that bag of chips or bottle of cooking oil starts to smell and taste kind of funky after a while. It's the same basic chemistry, a reaction with oxygen, just at work in 2 totally different parts of our lives.
So the big takeaway here is that chemistry isn't just something that happens in a lab with bubbling beakers. It's everywhere. From the green patina on a copper statue to the reason chip bags are filled with nitrogen gas to prevent rancidity. These reactions are happening all around you, all the time. So now that you know the clues, what are you going to notice changing tomorrow?